Welcome back into our exploration into trigonometry. This is the final concept that we're going to talk about. We're going to be working with dot products. The dot product is when you multiply two vectors together. We have done multiplication with vectors just by a scalar. So we've taken one vector and multiplied it by a constant and done what's called scalar multiplication. A dot product is when we are multiplying two vectors together. We do this by taking vector v and vector w, and we're going to assign vector v in component form to be the components a1 and b1. And we're going to assign vector w with the components a2, b2. And the way in which we calculate their dot product is we take the a components times each other, and we sum that with the b components times each other. So we have the vector v times the vector w is equal to a1 times a2 plus b1 times b2. When we do this, we're multiplying two numbers, adding another set of the multiplication of two numbers, and we get a scalar. This is not a vector result. We are getting a scalar result when we do this multiplication for a dot product. Let's talk about some properties of dot products now. Let's say we have vectors u, v, and w, and scalar c. When you take vector v times vector w, that is equal to vector w times vector v. When you have the multiplication of vector v times a scalar c times vector w, that's the same thing as that scalar c times vector v times vector w. Vector v times vector w plus vector u is the same thing as vector v times vector w plus vector v times vector u, essentially the distributive property. Vector v times itself is equal to the magnitude of vector v squared. The zero vector times vector v is equal to 0. Their dot product is the scalar 0. Scalar c times the dot product of vector v times vector w is equal to scalar c times vector v times vector w, which is also equal to vector v times scalar c times vector w. Looking at these properties, number one is saying that the order in which you do the dot product in doesn't matter. That's because you have the commutative property of multiplication. a1 times a2 is the same thing as a2 times a1. Property 2 is saying that if you take a scalar times a vector and then compute the dot product, that's the same thing as computing the dot product times the scalar, which is kind of like the associative property of multiplication. Property 3 is the distributive property. And property 6 also has that associative property component. Looking at this figure, we have vectors v and vector w that are tail to tail, connected by an angle theta. And because they're tail to tail, the distance between their tips is the vector difference between vector v and vector w. We can calculate the angle between them, and it's similar to the law of cosines. The way in which we find the angle theta is, first of all, by taking the inverse cosine of the dot product of vector v times vector w divided by the magnitude of vector v times the magnitude of vector w. If the dot product between vector v and vector w is positive, then that means that the cosine of theta is also positive. And if the cosine of theta is positive, then theta has to be in that first quadrant and must be between 0 and 90 degrees. If the dot product between vector v and vector w is negative, then the cosine of theta is also going to be negative, and therefore theta has to be between 90 degrees and 180 degrees. If the dot product of vector v and vector w is equal to 0, then the cosine of theta is also equal to 0, which happens when theta is equal to 90 degrees. And if this is true, we say that vectors v and vector w are orthogonal. Two vectors are orthogonal if, when they're drawn tail to tail, they form a right angle. Defining orthogonal, two vectors that are drawn tail to tail and form a right angle are orthogonal. It is also true then that their dot product is equal to 0. So if a vector times another vector, calculating their dot product, gives you a result of 0, then those two vectors are orthogonal.